Hello. So I assume I'm audible. So today I will discuss about linear transformation, orthogonal basis, projection, this topic. Okay. So before starting, if anyone has any queries regarding the previous week discussion, or even since you have already you have seen that those videos for today's week. So if you have any queries regarding today's discussion as well, before I start the discussion, you can ask so that I can start with that portion, or else I will do it accordingly by myself. So I suppose you have no queries. So I'll start with the linear transformation. So linear transformation is basically a mapping. It is basically, let's say, T is some sort of a mapping which takes the value of some space, which takes the let's say it takes the values or it takes the vectors from one space and it projected to, let's say, another space. So this mapping is basically considered as a linear. Means there is a no nonlinearity. Like since x square, x cube, we know these all are nonlinear terms. So when I'm talking about linear, like so if I take x and y, so if I take so let's say x, y, z, this is basically a vector which belongs to V. Now it takes the value, let's say I'm calling this vector as a V, and let's say, so what this linear transformation does, it takes the value, it takes this vector V, do some linear transformation, and how this W is defined. So W is defined is where, let's say, where the Z axis is basically, there is no Z axis. It is basically XY plane. So how this is, let's say, it plotted to some sort of this sort of plane. So if I'm considering a 3D picture, so this is Z axis, this is X axis, this is Y axis. So let's say somewhere here the point is basically existed. So somewhere here the point is basically existed, which I'm calling V. So this is basically a vector which has x, y, and z term, obviously, and it basically projected on xy plane. So it is basically projected on over here on this xy plane. So in this xy plane, there is x term, there is y term, but there is no z term. That's why this x, y, and 0. So let's call it a small w. So this sort of transformation happens. So it takes the value from one space and it projected to maps to the another space. So this, while we are doing this sort of this sort of transformation, there is a no nonlinearity. The nonlinear term does not exist over there. So that's why it is called a linear transformation. So there are a few rules of linear transformation. So when we are talking about linear transformation, so if the T is said to be a linear transformation, okay, if the first thing is T of V plus W is equal to T of V plus T of W, where V belongs to capital V and small w belongs to capital W. So what does it mean? So if we add the two, um, yeah. So if we add two vector from two different space, and then we do the transformation, which maps to another space, this is equal to if we do the transformation first of individual vector and do the addition. So we will get the same result. So this is basically define the same thing. And the next rule is, next property is, so T of alpha V is equals to alpha of T V. What does it mean? It means that where alpha belongs to some real number and small v is belongs to capital V. So, so basically, if we do the transformation of scaled vector, it is similar to that first we do the transformation of this vector and then we scaled it. Okay, so these are the two. So these are the two basic rule of linear transformation. So if we combine these two property, so the third property will come into this picture. So basically, if we combine these two property, it's not. I mean, there is basically a combination of third property, first two properties. So alpha v plus beta w is equals to alpha t v plus beta t w. So where v belongs to capital V, w belongs to capital W, and alpha beta belongs to some real number. So that is basically, so this one is the third one is basically the combination of the first two one. Okay. Now there is a catch in this case. So let's say if my transformation, suppose suppose if, let me write it properly. So let's say T is a transformation. Okay. I'm not saying whether it's a linear transformation, non-linear transformation, non-linear transformation. The answer will be, I mean, you will be the one who will give me the answer basically. So T is a transformation over here, and what type of transformation it is? So I'm saying, suppose T adds an affine part, affine number, let's say some x naught to every vector. Okay, so T basically it do the transformation. How it do the how it does the transformation? It basically adding when it when T do this T does this whole this transformation thing is basically add another term, another positive term, negative term, whether another affine term is basically add to the each vector, add to each vector. So whether is this a linear transformation? So we have to check that. So first of all, give me the answer whether what do you think that whether this transformation is basically a linear transformation according to this logic?
Sir, X naught is a scalar.
You can consider as a vector. I mean, it basically, I'm saying that T is when we T do this transformation things to each vector, like this V. Let's say when I do this transformation, when I do this TV, what it basically shows, it basically adds. So TV is basically adds a term, adds an X naught to that vector. So this is basically the transformation that I'm saying. So V is a vector which lies in, let's say, some vector space V. Okay. And TV is a another vector which lies another vector, maybe it may be in the same space, maybe in different space, I don't know. So I'm saying it lies in some space W. So when I'm doing this transformation, what basically T does, T is nothing but adding an extra element to the vector. That is T is basically doing. So whether this transformation is a linear transformation or non-linear transformation, I mean, what do you think? Is this property?
Sir, yes, it satisfies the linear transformation property.
Now we will see whether it satisfies the linear transformation property or not. So I just colored it. The first thing we have to check. Okay, so we have two vector. Let's say U belongs to capital U and V belongs to capital V are the two vectors. Okay, so these are the two vectors. Now I have to do the transformation. So first I have to do the transformation with U, right? So what if we do this transformation with U, what will get? U plus some X naught. Okay. Now if we do the similar transformation, what we will get is basically V plus X naught. Now if we do the transformation U plus V, what we will get? So this is U plus V is new vector. Okay. So we will get U plus V plus X naught. Okay. Now according to the first property, this T of U plus V should be TU plus TV. Now we have to do the TU plus TV first. TU plus TV. What we will get? U plus V plus twice of X naught, which is not equal to TU plus TV. That means the first property does not satisfy. This means T is not a linear transformation. So when an affine function or affine part adds over here, this is basically an affine transformation. So when an affine part adds over here, that means the system is the transformation, sorry, system not, the transformation is now become a non-linear transformation. It looks like, okay, it's something like I'm just adding a term. There is no square or cube or any higher order term over here. It's just adding a term, but it does not follow the property. Okay, so that means our transformation is not a linear transformation. So that's why uh, if you see uh, like y equals to mx is basically a straight line passing through the origin, right? This line satisfy all the linear properties. That's why this is basically a straight line or the straight line properties. That's why this is a linear term or linear function. But if we add an affine function to this system, y is equal to mx plus c. Now this is also a straight line, but it does not pass through the origin. This is basically a shifted version. So this, if I draw these things, so this mx plus c, let's say it may be something. It depend on what is the value of c, positive, negative, depend on. This is sort of y equals to mx plus c. This is a straight line, but this does not satisfy the property of linearity. So that's why this is not a linear function, right? So whenever the affine part added to the system or added to the function, it no longer become a linear because it does not follow the linearity. So similarly, if we do another short example, okay. So before that you know the Cauchy-Schwarz inequality, triangular inequality. You know the property of norm, right? So if you don't know, I'm just showing you. I mean, writing over here. Just a minute. So there are three type of uh, inequality or equality, you can say. The first one is Cauchy-Schwarz inequality. What it says the absolute value of inner product. So this is basically that angle bracket is basically the sign of inner product is less than or equals to, or you can write it over here, write it like that as well. Norm of VW is less than equals to norm of V to norm of W. The second is triangular inequality. It's same thing, which is in addition. Just a minute. So it is basically, it is better to write it over here. Write it something like that. It's not the right thing to say. Yeah, something like that. Okay. So these are the three inequalities. Sorry, two, and the third one is Pythagoras theorem. Which shows us V plus W whole square equals to V square plus W square if V and W are orthogonal to each other. So I will discuss about what is orthogonality. For that now, this is basically, this term basically defines that V is perpendicular to W or W is perpendicular to V, which is that V and W both are orthogonal to each other. So for the time being, you just accept that okay, this is the term. Okay. So now the question is, so the example says if this transformation I'm saying that TV equals to norm of V. Okay, so norm means, what is norm? So this is when I'm saying this norm means this two norm, that means base is 2. Okay, so this norm is basically root under inner product of V with V. That means V transpose V. We have to do first when I'm saying this inner product. This is means V transpose V. Okay. First we do the V transpose V and then take the root and we will get this kind of thing, which is called a norm, which is basically a scalar term. Okay. So this is the transformation that I'm saying. And the question is whether it's a linear or non-linear term. Okay. So the answer is no, this is not a linear transformation. Why it is not linear transformation? Because according to linearity, so TV equals to norm of V. We know that. Similarly, TU, if I take another vector, U, so it is norm of U, and T of U plus V is equal to norm of U plus V, right? So this should not be equal to this, right? Because TV plus TU, if I do this TV plus TU, this is basically norm of V plus norm of U. Because I did not say anything about whether V and U are orthogonal to each other or not. I haven't mentioned anything about the specified property of U and V. I'm just saying V is a vector from the vector space capital V, and U is a vector from the vector space capital U. And I'm saying that T is some sort of a transformation, which is something this norm transformation. And I'm saying whether this transformation is linear or not. So what we get TV plus TU is this V norm of V plus norm of U. But according to triangular inequality, so what it says, what triangular inequality says, this is less than or equal to, right? This is less than or equal to something, but it should be equal to always. So that means this does not satisfy the linear property. So that means our this transformation is no longer a linear transformation. But let's say if we do the rotation, let's say I have a vector something like that. I have a vector something like that. Okay. So let's say this is a vector V. Now, if I rotate this vector to this position, V prime. So this is also a transformation because I am multiplying a vector. I'm multiplying this vector V. I'm multiplying this vector V with a matrix, a particular matrix, which is known as a rotation matrix. And then I get this another vector, which is V prime. So this is basically also a transformation. So this transformation is a linear transformation because there is nothing non-linearity on that. Because I'm saying, okay, let's move this vector of angle some theta. Move this vector by angle theta. So that means this transformation is a linear transformation. So let me show you something. Uh, sorry. Sure. So for the timing, I'm just taking and stop presenting over here, and I'm presenting sharing my screen. Is my desktop screen visible to all of you?
No, sir.
Okay, only Teams screen is visible, right? Okay. Now it's visible to all of you, right? Desktop screen. So let's say I have a vector. We call it a house matrix, basically. So when I am here, basically each row are the x coordinate and each row are basically x and y coordinates. Okay, so the matrix is something like that. So this is basically online MATLAB. You have to access this online MATLAB, you have to I mean register for
It's
that.
not
I mean
showing, sir. It's not
my
visible, sir.
my MATLAB screen is not visible to you. Okay,
Hmm.
weird. I'm sharing my whole screen. Now it is visible. MATLAB screen. I think it is visible, right? Hello. Hello.
Yes, sir.
MATLAB screen is visible, right? Okay. Now it's a 7 2. So this is my matrix. Okay. So here each column are basically xy coordinates. So now if I plot this, if I plot XY plot, so I'm plotting all the rows with the first row with all columns. Sorry, what I'm doing. I'm taking, yeah, sorry, that's the thing. First row with all columns with second row with all columns. Oh, I did something wrong. Oh, sorry. So this is, let's say this is my matrix. Now I want to do the linear transformation. So so each vector is basically, so here basically all the columns are basically the vectors. I mean XY coordinate. Okay. So I want to rotate this whole house. So first of all, if I do this identity transformation means if I consider A is an identity matrix. Okay, so A is an identity matrix over here. Now if we do the transformation, let's say I have now the transformed matrix is basically H1, which is A multiplied with H. That means I am basically transforming each vector. I'm basically multiplying each vector, each column vector with A. Okay. So what I will get the same result. And if I plot this whole thing, H1, the view is same. I mean, the house is basically the same. Now I want to rotate this. So how to rotate it? Let's say I'm considering this is a rotation matrix. I want to rotate my rotate this figure 35 degree. So that means there's a cos D. So there is a cos. If you use cos, you have to use radian value at the angle position, and if you use D cos D, then you can use the degree value. So let's say I want to shift 35 degree. This is become my rotation matrix. Okay. Now if I do the transformation, let's say H2 is my transformation, new transformed vector, which basically each vector of H is multiplied with A matrix. So I will get a different H2. Now if I plot this H2, now if I plot this H2, so it is basically shifted by 35 degree, right? Now let's say I want to shift it in opposite side, like what is it? The shift something like I use some sort of this matrix. Okay. So previously I used identity matrix. Now I just exchange the row of this identity matrix, and I want this. Okay, what will be the rotation of that matrix? So so that yellow part, I hope you can see that yellow one. I plotted it on the same graph so that you can understand how this shifting is happening. So that yellow one is shifted to that right side, right? So this is basically the transformation basically are doing. This is basically transformation doing. So it's basically taking a vector linear transformation. So when we are talking about linear transformation, it's basically a matrix multiplication with a vector. So when we multiply a matrix with a vector, we get another defined vector. Sometimes we get the same vector, sometimes we get the defined vector. So when we get the same vector, there is a particular name for that vector, a particular name for that vector. We will discuss those things in the next discussion. Uh, so this is basically we are multiplying. So my what I'm trying to say is basically when we are doing linear transformation, we are basically multiplying a matrix with a vector so that we get a different sort of vector. And that rotation of this vector, that shift of this vector is defined in the column of this matrix. Okay, so this is how basically the whole rotation kind of thing is happening. Okay, I hope it is I mean, you can I hope you all understand what I'm trying to say. So I'm just stop sharing this screen. Okay, now move to my main screen over here. Okay. So it's a so the example wise, if we see, so there is okay, the elimination matrix, which is what is elimination matrix? This is called elimination matrix. Gives a transformation from xy to t of xy, and how it is defined? It is x comma x plus y. So, and the question is basically, so what will happen to the unit square something where x lies between 0 to 1 and y lies between 0 to 1. Okay. Now, if you see, so this is origin. So this is sort of so this is basically a unit square box. So what will happen if we do this transformation? Okay. So let's say t x y. So 0 0 will remain 0 0, right? According to this transformation logic, 0 0 will remain 0 0. T of 1 0, what will happen to t of 1 0? It will become 1 1, right? So T of 1 0, what will happen? Sorry, 0 1, what will happen to T of 0 1? It will remain 0 1. And what will happen to T 1 1? It will become 1 comma 2. So what will be the picture? 0 0 is same, 0 1 is same. Now 1 0 will become 1 1, and 1 1 will become 1 2. Right? So I will get something like this sort of picture. So that means my unit square is now tilted somewhere. This is TV is basically takes the vector from R2 and also mapped in R2, but in shifted version. So this is how this is how the transformation basically doing basically. Okay, so I hope it is clear to all of you. We will do in previous discussion we have considered that if V1 to Vn are the basis of a particular space V, then and A is a matrix. If I remember, uh, no, previous to previous discussion, yeah. So here we know that if V1 to Vn are the basis of Rn, and if A is a invertible matrix, then AV1 to AVn, these also are the basis, right? So similar. So what is A V1? I mean, what is basically matrix over here? This is basically one transformation. I'm taking the V1 from one space and multiply it with the matrix and shift it to the other place. Okay. Now takes derivative. Uh, yeah. Now do another example. The next example is, suppose T transform V1. There is a vector to T V1. So it's basically taking the vector from 2D space and plot it or mapped it in a 3D space. And suppose the second vector V2, which is 0, 1, goes to PV2, which is 5, 5, 5. Okay. So then what is the matrix A? I mean, that means there is some sort of matrix which is multiplied with V1 and V2 and giving this TV1 and TV2. So what is basically the matrix, and whether this also this is a linear transformation or not, we will see. So first of all, this is here V1 and V2 belongs to R2. Okay, and TV1 and TV2 belongs to R3. So from here we can see that it takes the value from R1 R2 and map to the R3. So what will be the matrix dimension? So therefore the dimension matrix A the dimension of matrix A should be 3 cross 2 because it takes the value, it takes the vector which is size 2, that means the row should be size 2, and it places to the size 3. I mean that maps to the size 3. So the column should be column should be size 2 and the row should be size 3. So since it's a 0 1 and 1 0 and 0 1, so the matrix the matrix should be something like that. Right? So this means 2 3 4 multiplied with 1 over here, and I mean this 0 multiplied with 5 5 5. So obviously we will get 2 3 4 for the first column. Similarly, this is not exactly equal to, this is sort of, I'm just dividing it somewhere. And the second thing is, normally if this is a matrix A and this is a vector, let's say V, and since this is the identity matrix, so obviously we will get this term. Okay. Now, derivative. So derivative and integral, these two are also linear transformation. So here in this case, is basically we are talking about, let's say we have a function something like that. We have a function something like that. 1 x x square x cube. Okay. So derivative. So first of all, I'm just shifting it somewhere else. So how this derivative works? So whether it's a linear transformation or non-linear transformation, we should check that first. So let's say I'm doing derivative with respect to x, and this is alpha v plus beta w. So this is something like, if we do this derivative, this is similarly dv dx plus beta into dw dx, right? We can split it something like that. So that means this is a linear transform. This satisfy this t v. This is something like this. So that means our derivative is a linear transformation. Now I have a function something like that, or you can say this is basically a vector sort of. So it's, what will be the derivative? So its derivative basically right. So what would be the matrix form of derivative t? So what would be the What will be the matrix form of derivative t? So let's say if v is equals to something like a plus bx plus c x square plus dx cube, with derivative is dv dx is something like 0 plus b plus 2cx plus 3d x square. So what would be the matrix of this derivative? It is something like, since here you can see there is a cubic polynomial and this is a quadratic polynomial, right? So that means our term should be something like I'm calling this as a so ultimately here we get b 2c and 3d. So that means when I'm talking about cubic polynomial here, for the basis for the cubic polynomial, what are the basis for the cubic polynomial? The basis are 1 x x square and x cube. So all are linearly independent because we cannot produce one by other using that linear combination. Okay, and basis for quadratic polynomial function are only 1 x and x square. So that means dimension, we are basically reducing the dimension from dimension 4 to number of bases in the basis vector is basically the dimension of that space. So this belongs to, let's say, vector space V, which has a dimension of R4, which is basically the, let's say, subset of R4. And this belongs to the basis, belongs to some vector space W, which is basically the subset of R3. So that's why our matrix is become 3 cross 2 matrix, because we are basically reducing the uh, dimension. In previous case, we are increasing the dimension. That's why our matrix become a tall matrix. But here we are reducing the dimension. So our matrix is now become the fat matrix. Okay. So basically that's why, since this is a basis, so V is any vector in this vector space capital V, where all A, B, C, D are the uh, constant term, and 1 x x square x cube. So this is these are the bases. So this is the linear combination. Any vector in that vector space should be the linear combination of the basis vector. Similarly, dv dx. So here dv dx is another vector in vector space W, and it is the linear combination of this three terms. This b 2c and sorry 1 x and x square, where the coefficient are b 2c and 3d. Okay. So till that point, similarly integration also, because integration is basically inverse of derivative, right? So it is also, integration is also a linear transformation. Okay. we sort of move to the next segment. Now we move to the next segment, and the segment is basically, so up to that point is clear to everyone, right? I hope up to that point it is clear to everyone. Now, the concept is, let's say we have an ordered basis, call it B, which consists of, let's say, V1, V2 up to Vn vector in Rn dimension. Okay. V is basically the vector space, which is a subspace of dimension n. Okay. And let's say alpha 1, alpha 2 up to alpha n, all are the real numbers and all are different. I mean, alpha 1, alpha I is not equals to alpha j. And if any vector small v belongs to capital V, if we can write any vector small v, if we can write any vector small v which belongs to capital V, we can write it as a alpha 1 v1 plus alpha 2 v2 up to alpha n vn. So we can write these whole things in this format. V at ordered basis B alpha 1, alpha 2 to alpha n. This representation suggests that this alpha 1 is multiplied with V1, alpha 2 is multiplied with V2, and similarly alpha n is multiplied with Vn. So this is called coordinate vector of capital V. Okay. Now there is a catch. Suppose we have two vector space V and W. Okay. And T is a set of all linear transformation from V to W. That means T is basically the set of all the linear transformation which takes the value from V and maps to W. So T1, T2 belongs to this capital T. Okay. Now the basis, okay, the term basically you should know that when we are mapping from this V, I mean we are mapping from V and map to W. So from which space we are basically mapping is called a domain space, and where we are basically mapped to in which space, that space is called codomain. So V here is a domain and W here is a codomain. Okay. Now if the basis for domain is equals to, let's say, V1, and basis for codomain is equals to V2, then property says if we do if we add this transformation first at domain codomain, let me just check. Sorry. Domain to codomain, then it should be equals to b1 b2 plus b2 b1 b2, and similarly alpha is any vector, any scalar b1 b2 is alpha of t1 is b1 b2. Now we will do an example from this. So example says T is something which mapped from R2 to R2. Okay. There are two transformation T and S from R2 to R2. So T of xy defined as something like 2x comma 3y. So this is the transformation. Okay, it takes the value of xy and it mapped to 2x and 3y. And S of xy is something like x plus y, x minus y. Okay. Now you can check whether this T and S both are the linear transformation or not. You can check it by yourself. And let B is the basis of domain, which consists of 1 1 and 0 2. B1 and B2 is the basis of codomain, which is standard basis, that is 1 0 and 0 1. Okay. Now we have to verify whether this property satisfy or not. That means we have to verify that T plus A domain. So B1, B2 is equals to T B1, B2 plus, sorry, this should be S B1, B2. Okay. So now T of x comma y equals to what is 2x and 3y. So in the domain basis, so if we do 1 comma 1, what we will get 2 comma 3. Now in codomain space, we can represent this vector with the basis vector, right? We can represent this vector with this basis vector. So what would be this? So 2 is multiplied with 1 comma 0 plus 3 is multiplied with 0 comma 1. So this is basically vector. So we will get this 2 comma 3, right? Similarly, 0 comma 2 is basically 0 comma 6. So we can represent in codomain space with the basis vector. So that means what would be the T this matrix? What should be this matrix in codomain space? What should be this T of B1, B2? This matrix is 2, 3, 0, 6. Okay. Similarly, if we do this S x y, which is x plus y and x minus y. Now in domain space, it was 2 comma 0, which we can write, and in codomain space we can write it, what the value, 0 2, it's 2 minus 2. It means 2 into 1 comma 0 plus minus 2 into 0 comma 1. So what is your S of domain to codomain space matrix? It's 2 0 2 minus 2, right? Now we have to show that now T plus S x comma y, according to the linear property, what should be this? T x comma y plus S x comma y, right? Because we know that T and S both are linear. So T is basically 3x, 2x, 3y, and S is basically this term. So this is basically 3x plus y, and this is basically x plus 2y, right? Just normal vector addition. Now we have to do this whole things. T plus S. Now 1 comma 1 in domain space, we can represent it. This is 4 comma 3. So we can represent it in a codomain space in that format. Now T plus S 0 2 so T plus S from B1 to B2, what we get, the matrix is a 4 3 2 4. Now we have to do these two addition, and we have to check 2306 plus 202 minus 2. So 4 2 3 4, which is equals to T plus S B1 to B2. That means our property has been verified, right? So now next move to the orthogonal basis. So first of all, what is orthogonal? So what is orthogonal vector? So orthogonal vector means if the two vectors are perpendicular to each other, that means just a minute. So when we say that two vector, if you given, if let's say suppose V, you have given V, let's say there some sort of element over there, and you have given W. Okay, there are sort of element in that vector. Are the two vectors, right? Now, are they orthogonal or not? That means whether how do we compute the orthogonality of these two vector? How do we find out the orthogonality of these two vector? Like you are given that okay, these are the two vectors, and whether these two vectors are orthogonal to each other or not. So in that case, if the dot product of V and W, which is basically the V transpose W, is basically 0, This signifies orthogonality. That means these two vectors are orthogonal to each other. So if if the vectors are orthogonal to each other, in that case, that Pythagoras theorem that satisfies, that is v square plus norm of w square is equals to norm of v plus w square. Okay. Now, in case we have studied previously, we have studied in previous discussion as well, that there are four spaces, four subspaces, right? What are the four subspaces? It's a row space. Second, we have studied column space. Row space, the space spanned by the rows of a matrix A or a many matrix. Column space are the space that are spanned by the matrix A, and they're spanned by the columns of matrix A. Third, null space. Null space means the space that are spanned by the vectors which gives the solution Ax equals to 0. And the fourth one is basically left null space. What is left null space? So after taking the transpose of matrix A, now we have to find out the null space of that matrix. So it is called left null space or null space of A transpose. Okay. Now if you see when so when we do Ax equals to 0, so here what we do, we are basically trying to find out the solution of this solution of this equation, and this set of solution gives us the space. And it gives us basically the basis of that space, and we can span we can span the whole space by the linear combination of this basis, right? Now, if you see, the matrix is something like this format. Okay, so let's say I'm considering x1 and x2, and here one term, second term, third term, fourth term, and I'm getting 0, 0. So how this multiplication happens? So multiplication basically happens uh, something like that, right? Row and here column, right? So what we can see, this is just a pictorial representation. This is not the exact. I mean, you can understand that what I'm trying to say after that. So basically, you can see that row space is multiplied with something like that, and we get the null space. So that means row space is perpendicular to null space. Similarly, if we do the let's say I'm giving this 2, 3, 4. I'm just giving it number. Now, if we do the A transpose of Y and try to find out the null space for that. So what is A transpose? A transpose is something like x1, x2, star 1, star 2, star 3, star 4. And here it's y1, y2, and here I'm getting 0 over here, right? So multiplication is something like this. So that means row is multiplied with this column. That means row space of A transpose is perpendicular to null space of A transpose. That means column space is perpendicular to always left null space. Okay. Okay, before that, before move to the projection part, I just want to, I just forget to give another example from the previous linear transformation. Just let me do that. So, what it say, using standard basis, find the 4 cross 4 matrix P that represent a cyclic permutation T from x equals to x1, x2, x3, x4 to T of x equals to x4, x1, x2, x3. Okay. So what question says? Question says that we have to find out the matrix P, which basically do this whole transformation. How this transformation happen? We first take the so this is basically the matrix. This is basically the vector that needs to be transformed. This is basically the vector that needs to be transformed. Okay, and transform to this vector. So where the first element should go to the second, second should go to the third, third should go to the fourth, and fourth goes back to the one position. So this is basically the a cyclic permutation should happen. So what should be the matrix? That matrix P. So from here you can see that okay, I have to find out a matrix P which takes this vector and generates this vector, right? So it is very easy that x is x4 is moved to the first position, right? So that means the first position, the last position should be 1 and other position should be 0. So in that case, x4 move to the first position. Now x1 move to the second position. So that means the first one in the second column, second row, the first element should be 1 because I'm going to take the first element. I'm concerned about the first element. I'm concerned about the other element, and other elements are 0. Now in the third column, it should be something like that, and the fourth column, it should be something like that. So this is basically the P matrix. So this should be the P matrix which makes the vector cyclic in nature. Now if we do another transformation, what will happen if we do this P of x? So what will happen? The structure will become x3, x4, x1, and x2. This will be a cyclic nature, right? So that means you have to do again, you have to do the transformation. What transformation? The same P matrix you have to multiply with this vector, right? Because you have, right? So this is x and this is T of x, right? Now you do the transformation on T of x and you get some sort of T square of x, right? So now the here the vector is x4, x1, x2, and x3. And what I'm getting is basically x3, x4, x1, and x2. So the same P matrix, the matrix should be same because x3 is moved back to the x1 that first position. Then the first position should move to the second position element move to the third, and third position element move to the fourth. So that means this is also a P matrix. So that means if we multiply P square with x, we will get some sort of T square of x, right? Now this x means the previous element. So if we multiply p square, if we multiply p with p and we get a matrix which multiply with the x, that is the original vector, then we get the double transformation. Now if we do again transformation, you will get a x2, x3, x4, x1. Okay. Now if we do the fourth time transformation, you will get the identity matrix. So this is basically, these sort of matrix are called a permutation matrix, because we are basically rearranging the elements of the vector, inside the vector. We are basically permute the elements of the vectors over here. So that's all about this. Now we do the we will see the projection and then we will wrap it up. Up to that point, if anyone have any question, any queries, kindly ask. I'll be happy to answer all these questions. So let's say I have a vector. So let's say I have a vector B, which is 2, 3, 4. Okay. Now, what would be its projection on Z axis and on XY plane? So I have a 3D vector something like this. So this is sort of, this is a B vector. Okay. Which coordinates that is given to us 2, 3, and 4. So what would be the projection of this V vector on Z axis? When I am projecting completely this vector on Z axis, that means this is the projection, right? This is the point. Let's say I am calling it BZ. Okay. So what will be the coordinate of this point? This coordinate of this point should be something like 0, 0, and 4, right? So the projection of this B vector on Z axis is, we will get this point. Now projection of B vector on XY plane, what will be the projection? Let's say this is XY plane and this is the vector that I'm getting and I'm calling it BXY. And what is the coordinate point of this XY plane? It is 2, 3, 0, because here no Z axis existed. So the projection of B on Z axis is 0, 0, 4 and projection of B on XY plane is 2, 3, 0, right? Now how it is happening? So BZ is basically some P matrix, some projection matrix that I'm going to use over here, which is multiplied with B. So what is the projection matrix P1? The projection matrix P1 is basically consists of only one element, right? This is 2, 3, 4. So 0, 0, 0, 0, 0, 0, and 0, 0, 1, right? That's why I'm getting 0, 0, 4. Okay. Now projection of B vector on XY plane, there is another matrix P2B, which is 1, 0, 0, 0, 1, 0, and 0, 0, 0. Because we do not need any Z axis, because we are projecting on XY plane. 2, 3, 4. It's 2, 3, 0. So the difficulty is we have to find out this P matrix somehow. So it is very easy. Sometimes it is not that much easy. That define this P matrix, that projection matrix is not that much easy. Okay, now we have to define the P matrix. Okay, now projection on a line, if I am saying that means I have something 2D plane X and Y, and let's say this is the line that I'm concerned about. This is line, let's say a vector, and I am projecting this B vector onto this line. So what would be the projection? So this part is basically the projection of this part is basically the projection of B vector onto this line. Okay. Now I will finish it with this term. I'm going to discuss it. I'm not going into detail of projection because we will study projection on the next class. So we will. I'm not going into detail of this projection. Just to introduction part. So this is basically the vector P is basically the projection. So when we are talking about projection, we are talking about the shortest distance of the vector to the host plane or host line. So this is the vector. Okay, this is the vector B that we are basically we are concerned about, and we need to project this vector B on some line. So this is the line that is vector A, and we need to find out the shortest distance. So perpendicular distance is the shortest distance, right? So this is basically the shortest distance, and we need to find out this projection, the P. So how to find out? So this term is basically the error term, right? That means this vector, this this vector we are projecting over here. So obviously we are not getting the exact value of B. When we are projecting some vector onto some plane or onto some another space, we are not getting the exact value. We are getting the similar value. It's like something like when we are not getting when the system of equations are not I mean what I'm trying to say is like the system of we are not getting the exact solution of the system of equations. So sometimes like tall matrix over there, like more there are more number of equations than the variables, and we are not getting the exact solution of the that particular system of equation. We are just find out the least square solution. So I hope you have heard about this term least square solution. Least square solution means shortest possible distance, the nearest distance. We are basically trying to find out, okay, this is the nearest possible solution which satisfy all this equation. Okay, this is the best case solution that we are basically trying to find out. So this is basically the error term. So how this error is defined? This is basically B minus P. Okay, so that means this B minus this P, this small p. Okay. Now, as you can see, I'm calling it as a E vector. So as you can see, that error is perpendicular on A, right? So let's say so this is A vector. It is basically consist of this element AN. Okay. Now P is the closest to B vector, which is basically consist of this element. Okay. Now the error E is perpendicular to A vector, right? Perpendicular to A. Now what is E? E is basically, now since this P is this P basically lies on this A vector. P is basically lies on this A vector, right? So that means we can represent this P vector by the basis of this A vector, right? So we can write that P is basically, let's say, x1 hat A1 plus x2 hat A2 plus xm hat AM, right? Sorry. This is my mistake. Sorry. So this is not a basis vector. This A is not a basis vector. This is a vector. So P here, P is basically multiple of A, because P is basically the part of A. So we can write P as a sum x hat into A, right? Now the error vector E is basically B minus P, which is B minus x hat into A, right? Now, as I said that E is perpendicular to A, which implies that E transpose of A is basically 0, right? So that means B minus x A transpose A equals to 0, right? So what it should be, it is basically B transpose A minus x hat A transpose A, right? So B transpose A, B is a vector, A is a vector. So B transpose A is similar to A transpose B, which is equals to x hat A transpose A. So from here, I get the multiplier term which is x hat equals to A transpose B by A transpose A, right? So now P, what is the multiplication term? This P is basically A transpose B by A transpose A into A, right? Yes. Just a minute. So this term, as you see, this term is basically a scalar term, because the top one is scalar, the numerator and denominator both are scalar terms. So we can write it in that format. P equals to A into A transpose B by A transpose A, right? So we can write it A transpose by A transpose A. So we can write it this division term, because this, the denominator A transpose A is a scalar. This is multiplied with B. So that means the projection matrix, this is basically the projection matrix. So the projection matrix is 1 by A transpose A multiplied with A transpose. A transpose is a matrix and this is a scalar. So I'm just stopping my discussion over here. We will discuss this projection thing on the next chapter and next discussion. Yeah. Let's say before stopping it, I'm just doing one example of the projection over here. It's a project B onto A to find P equals to A x hat. So we need to find the p small p, right? So we know that A, we know the formula. We have A and B over here. What projection matrix? Capital P is basically A transpose by A transpose A. So A transpose A, what is A transpose A? 9. Okay. Now A transpose so what is the position matrix? It's 1 by 9, 2 by 9, 2 by 9, 2 by 9, 4 by 9, 4 by 9, 2 by 9, 4 by 9, 4 by 9. Now small p is basically capital P into B. So this is 1 by 9. B is 1, 1, 1. So it's a 5 by 9, 10 by 9. And this is 10 by 9. So this is basically the projection. So that means if we see the picture, so something like that, this is X, this is Z, this is Y, and this is X. We have 1, 1, 1, something like this is 1, 1, this is something 1. So let's say this is 1, 1, 1. And we have another line 1, 1, 2, 2. This is something like this is B vector, this is A vector, and we are trying to project this thing, right? We are trying to project this. So this is basically the small p. Okay. This is basically small p, and that small p is basically 5 by 9, 10 by 9, 10 by 9. Okay. So up to that point, anyone have any query? So since you don't have any query, so I'm just stopping my recording over here. Okay.
Sir, slide
Yeah.
ଟିକେ previous slide ନେବେ ଟିକେ.
This one.
Yes, sir.
Ah.
So,
Yes.
जो T is from the R square to R2 to R2.
So which one?
Projection orthogonal ro previous example. Previous example of orthogonal.
Previous example of orthogonal. Okay. This one.
Yes, sir. Yes, sir.
Okay. Yeah.
Sir, you take B1 is the basis of domain 1, 1 and 0, 2. How it is possible, sir?
How is it possible? Means? It's I mean this 1 1 and 0 2 you they are the linearly independent, right? Because you can't express 1 1 single-handedly with 0 2. You can't express 0 2 single-handedly with 1 1. Because if you see that 0 2, the x element, there is no x element, right? And if you see 1 1, there is exist x and y both. So that means we can say that these 1 1 and 0 2 are linearly independent and they can span the whole space. They can span the whole space, right? 1 1 and 0 1. Let's say instead of 0 2, if it's the 0 1, so it can span the whole space. So 0 1 is basically the scaled version of 0 2, downscale version of 0 2, right? So 1 1 and 0 1 are the, I mean, if you remember the definition of basis, so it's basically the number of the number should be exact and there should not be any vector which are linearly independent with each other or any of other, and they should span the whole space. If the number is exact and all the vectors are linearly independent, then they always span the whole space. So I'm considering here basically this is the domain space R2. And if you remember when we talk about basis, basis is not unique one. Basis can be anything. Like in R2 case, the standard basis is 1 0 and 0 1. This is the standard basis. Okay. But also 1 0 and minus 1 1. This is also a basis. Right? This is also a basis. But you can't consider minus 1 0 over here. This is not a basis because minus 1 0 is basically linear combination of 1 0. So you can, if you choose this term 1 1 and here minus 1 1, this is also a basis. This is linearly independent. But if you choose minus 1, this is not a basis. This two are not basis. So the when you choose basis, you have to consider three things in your mind. First of all, the dimension of the system. If dimension of that system or dimension of the space is 3 or 4, let's say if you're talking about R3 space, so in basis there must exist 3 vectors, and those 3 vectors are linearly independent or dependent. So those 3 vectors, first you check that those 3 vectors should be linearly independent. And if they are linearly independent and number are exact, then they can form a space. They can span the whole space. Now, if I'm talking about R3 space, and I'm saying that okay, the basis consists of, let's say, 1 1 0 and 1 1 1. So can we say this is a basis? No, this is not a basis because number is not exact. This is not a basis for R3 space. This is maybe basis for the space which span by these two basis vector. But for R3 space, we need another vector, and that vector should be linearly independent with each other. So if we add another vector over here, then we can say, yeah, then we can say this is a basis. Okay. Now, is this your
Sir,
query or
okay,
there is something? Sorry.
Sir, can I take the B1 basis is 1 0 and 0 1?
No, that is I mean, if it is said in the question, okay, B1 basis of the domain basis is 10 and 01, then it's okay. But it does not say anything about that. I'm just saying the question already mentioned in question. It is already mentioned that the basis of the domain space, this is R2. So TS is basically taking the value from R2 and place it in R2. Okay. So you are just confused with these two terms, right? So this is R2 space. So from somewhere I'm taking this value. This is the R2 space, and I'm taking a value somewhere, use some transformation and place it somewhere in the same space. Now, and this domain range, when I'm talking about this domain range, the domain consider this is as a basis, and the codomain range or a codomain space, which is also a subspace of R2. Domain space is also a subspace of R2. Codomain space is also a subspace of R2. So let's it's better I write it not like that. I should write it something V to W, where V W is a subspace of R2. I think this is much more clearer. So V is a domain, W is a codomain, but both are in R2 space. Both exist in R2 space, but both space are different. They are not same space. Now I'm taking the value of value from V, and the basis for that domain space is 1 1 and 0 2. That I'm saying. It's not necessary. This is not an unique basis. Okay. You can consider any, I mean, there exists anything. But I'm saying, okay, B1 that I'm giving to you, that basis for domain that I'm giving to you is 1 1 and 0 2, and basis for codomain that I'm giving to you 0 1 0 and 0 1. Definitely from here you can see that you have to check that whether 0 1 and 1 0 can be the basis for the V space or not. It is also exists in R2, but you have to check all those criteria that whether this happens or not. Definitely you can see that both are exist in R2. So 1 0 and 0 1 both are basis for V and W as well. Similarly 1 1 and 0 2 both are basis for W and V. Similarly 1 1 and 0 1. These two can be the basis for both W and V because both are exist in R2 space. But here I have already mentioned that this is the basis for V and this is the basis for W. Now you have to, using this basis, you have to find out you have to verify this property. There is nothing like that. I mean, I hope, I mean, what basically confused you? I just don't understand. I mean, what makes you what creates the confusion? I'm just trying to understand what is basically your confusion. Like, this is basically what
যে
I'm saying.
B1 and B2
B1 and B2.
B1 and B2 মানে previously given এটা given দিয়েছি এটা
Yeah. It is given. It is given to the it is given to you. Like you have to compute according. You have to verify accordingly. This is given to you. Okay, I'm using when I'm playing with a domain space. I should use this is as a basis, and when I'm playing with a codomain space, I should B2 as a basis. Okay. This is just given to you. Like you have already mentioned, you have already I mean given that B1 is the basis for V. Like when you are dealing with a domain space, you should consider B1 as your basis. Okay. And this is given to you, and this is not unique one. I mean, using this basis, you have to find out. This is the question says. You have to verify using this basis. Obviously, according to the definition of basis is not an unique one. Basis can be anything, right? This is not a unicorn. It should span the space and it should be linearly independent. These are the two factors that should be followed by basis vector. Okay. This is just a question. I mean, there is nothing to worry about. I mean, nothing to confuse with all those things. Okay.
Okay, sir. Okay, sir. Again.
Okay then. So here I'm wrapping up this discussion. We'll see in the next week. Okay. Bye.
Thank you, sir.